This is the screencast for section 2.8, example 2. We're going to solve a polynomial inequality analytically. So again, we got to use algebra, no calculator. However, this problem is a third degree polynomial is greater than 0. Well, this third degree polynomial is unfactorable, so I do have to use my calculator and go back a couple sections to when we would find what zeros would be worth trying, do synthetic division, and factor this polynomial to get a hold of what our zeros are in order to be able to test them on the number line. I have done that already for us. I graphed 2x cubed minus 7x squared minus 10x plus 24 in my calculator, and I can see that it looks like -2, 3/2, and 4 are good zeros to try, and it's true. So 4 and -2 are zeros, and then I get the last one is 2x minus 3 as my the rest of the polynomial there. So that would make 3/2 my third zero. So those are the three numbers I'm going to test on the number line. So I'm going to pick any number left of -2, so -1,000 maybe, and plug it into each one of those to decide whether, or to determine whether they are positive or negative. So that would be negative. My number plus 2 would also be negative, and twice my number -3 would also be negative. A negative times a negative is a positive, times another negative is a negative. Now if I plug in -2 to this whole polynomial, the polynomial would equal 0, so I'm going to put a little 0 below the -2. Pick a number between -2 and 3/2. The easiest number between a negative and a positive is 0. 0 minus 4 is negative. 0 plus 2 is positive. 2 times 0 minus 3 is negative. A negative times a positive is a negative, times another negative would be positive. Pick your favorite number between 3/2 and 4. Mine would be 2. 3 will work. 2 minus 4 is negative. 2 plus 2 is positive. 2 times 2 and then minus 3 is positive. So a negative times a positive is a negative, times another positive is still negative. Oh, I forgot to write underneath. 3/2 is also going to make the function 0. So is 4. So I may as well write those underneath. Then any number to the right of 4, like a billion. A billion minus 4 is positive. A billion plus 2, positive. 2 times a billion minus 3, positive. So overall we get positive values here. And you can see that actually on the graph. You can see that the y values are negative to the left of -2, as well as between 3/2 and 4. They're below the x-axis. Then between -2 and 3/2, those y values are positive. And then again after 3/2, or excuse me, after 4, those y values are positive. So this inequality is asking for what x values makes that polynomial greater than 0, not equal to, greater than 0. So the final answer would be, let's see, not -2, but anything between -2 and 3/2, not including 3/2. -2 and 3/2 make it equal to 0, not greater than 0. And then again, anything from 4 to infinity, not including 4, because 4 makes the polynomial 0. The now try problem for example 2 is number 11. Same situation. We need to complete the factoring if needed, which yes we do, absolutely, and solve the polynomial inequality using a sign chart. And then we're going to support that graphically, which means we're going to make sure that our answers actually do appear either above or below the x-axis according to what the graph shows. My first step is to graph this polynomial in my calculator and decide what zeros are worth trying for synthetic division to begin to factor the polynomial. Then we can find out what numbers to test on the number line. So I did that. I graphed the polynomial on my calculator. I see that -2, +1/2, and +3 are zeros. So I put those through synthetic division just to be sure, and I got +3, -2, and 1/2 to all be zeros. So those are the numbers I'm going to try on my number line. So I put -2, 1/2, and 3 on the number line. I put zeros below each of those because each of those values make the polynomial equal to 0. And now I need to test something to the left of -2, so -500 maybe. So -500 minus 3 is still negative. -500 plus 2, still negative. -500 times 2 minus 1, still 500, or still negative. So negative times a negative is a positive, times another negative is a negative. Easiest number between a negative and a positive, so between -2 and positive 1/2 is 0. 0 minus 3 will be negative. 0 plus 2 will be positive. 2 times 0 minus 1 is negative. A negative times a positive is a negative, times another negative would be a overall positive y value that would be produced out of any x value between -2 and 1/2. Easiest number between 1/2 and 3, I think, is 1. 1 minus 3 is negative. 1 plus 2 is positive. 2 times 1 minus 1 is positive. That's going to result in a negative y value. Any x value I plug in between 1/2 and 3 will result in a negative y value. And last but not least, anything greater than 3 is going to result in all positives, which will be an overall positive y value. So now, as I'm looking at my graph, I am going to verify, I'm going to support graphically my results. I see that anything to the left of -2, any x value to the left of -2 is going to result in a negative y value, which is true. They're below the x-axis. Also, any x value between 1/2 and 3 is going to produce a negative y value. There they are. Which means anything between -2 and 1/2 is going to produce a positive y value above the x-axis. Any x value greater than 3 is going to produce a positive y value above the x-axis again. Now in this problem I'm looking for greater than or equal to. So I am in fact looking for those zeros. So the final intervals are -2, including, because -2 does make the polynomial equal to 0. So between -2 and 1/2, including both of those. And then again from including 3 to infinity. Any x value within those intervals will produce a positive or equal to 0, so greater than or equal to 0 y value.